The rates are the same. Good. So everything that's in equilibrium is when your rates are the same. Then it says what are the three possibilities from a concentration standpoint for equilibrium. Because in all equilibrium situations, the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, but there are three possibilities. You could have more products at equilibrium, you could have more reactants at equilibrium, or they could be equal. What is the most unlikely? Equal. Do you guys understand why that is the most unlikely?
Because it's only one thing, and there's a lot of other things.
There's a lot of other possibilities. It's like entropy. Right? Is it more likely for your room to be clean or more likely for your room to be messy?
Absolutely atrocious.
Because there's more possibilities to be messy than to be in an ordered position, right? What's that? But yeah, but you have to order it.
Order it off.
All right.
Amazon. I didn't have a room.
So, I don't know if you guys are making the connection quite yet. Shh. If you're making the connection quite yet, how this equilibrium chapter is related to the chapter we just did. What in this equilibrium chapter is so important from last chapter? What would you say? Rates. How fast? Doesn't rate and how fast have a big part in equilibrium?
Yeah.
What is the definition of equilibrium?
Balanced forces.
No.
Oh, I got it.
Chemical equilibrium.
When the rate of the forward reaction is equal to the rate of the reverse reaction.
Notice the key words there.
Rates are
Rate. What did we talk about last chapter? Rates.
Laws.
Okay? So if you look, okay, let's say this is the rate law for the forward reaction. Just a generic rate law for a forward reaction. Right? Okay? And this is the rate law for the reverse reaction. So the reaction would be A plus B gives you C plus D. Forward reaction, right? Right? These are the reactants of the forward reaction. But what is technically the reactants of the reverse reaction? They're the products of the forward, right?
That is where I got confused and added them on the test instead of multiplying. Because it looks to me like that.
Because I put a plus sign between a balanced chemical equation. Okay? So, if we said we are at equilibrium, what is true?
You can go back to them or the back. Those are equal.
This equals this. Yes?
Yes.
Means that AB equals.
No, be careful. Doesn't mean that AB equals CD.
Oh, the reaction rate's equal to the reaction.
Right? Because we could have a variety of different concentrations in being at equilibrium. We could be product favored, we could be reactant favored, we could be equal. Could be equal, but very unlikely. Right? So if I take the two rate laws and I set them equal to each other, I get this.
And K is different.
Okay? Gotta do a little manipulation. And if both these are constants, then taking a constant divided by a constant is a constant. Remember, what are we saying is true about this situation?
They're equal.
It's at equilibrium. We're at equilibrium. How do I know that? That, correct? Okay, we are at equilibrium. Okay? So I'm hoping you'll be able to see something here known as the equilibrium constant. And we're going to do this. Okay? So at equilibrium, could I figure out what the concentrations of my products and my reactants were at equilibrium?
Yeah.
Okay? And if at equilibrium things aren't changing, wouldn't the ratio of my products to reactants always give me the same number? Right, we said at equilibrium, you don't see any change, right? Okay, so if this isn't changing and this isn't changing, then for any chemical reaction at equilibrium, the products divided by your reactants gives you one constant, and one constant only. That's important. It's known as equilibrium. So an example example, so the equilibrium constant for this would be this, Ke cubed. And I will show you how to do this in a sec. I know I haven't done that yet, but I want to use this to explain the bottom two bullets. This would be the equilibrium expression for this particular reaction to find the equilibrium constant. And again, as we progress today, I'll start showing you more and more about this. But I want to make something very, very clear. It says at the bottom, when the equilibrium constant is greater than 1, what is true?
Forward reaction.
What did we say happens when the forward reaction is favored?
It goes, there's more condensity
Density.
We get more
Smart.
product.
You get more products.
At equilibrium, at equilibrium you have what? More products. Okay. If you said the forward reaction is favored, when you reach equilibrium, you have more what? Products. Where are my products up here? See, top, okay? Right here. So if I have more products than reactants, a big number divided by a smaller number, won't you always get a number that is greater than 1? That is important conceptually because you can learn a lot if I give you a number. If I say the equilibrium expression is, equilibrium constant is 120 versus the equilibrium constant is 4, they're both product favored, right? Because they're greater than 1. But which one goes further or closer to completion? The top one. So just looking at the constant can tell you a lot about a chemical equation and where its equilibrium lies. Does that make sense? Okay? Important conceptual piece that you should be able to get out of the math. Okay? And I'll show you again. I'll show you how to do the equilibrium expression here in a little bit. Okay? So then it would make sense if the reverse reaction is favored, I would have more reactants than products, right? So big number on bottom, small number on top. So I was going to give you a number that is large, less than 1. Large, less than 1 number. All right. So how do we do it? How do we do it?
Write it like you just wrote it up on there, or maybe just like
Oh.
yeah, seriously.
Like 3 of each.
That was so last year.
Okay. So here's the generic template of it. I don't know if you guys have a space for this. Do you have? Okay. I guess you'll find that this isn't overly difficult, but let me show you how this process works. For equilibrium, to write the equilibrium, all right, first off, I'm going to slow down. This whole thing has a name.
It's called the equilibrium equation.
This is called the equilibrium expression.
Where is this?
I want to see this.
Are we supposed to write this?
What? Draw it in.
What's the difference between an expression and equation?
I don't know. Well, like, the expression comes from the equation.
So we write this in. Can I take a picture?
Yes, I would write this in. The whole thing is called the equilibrium expression. I'm drawing blank.
EXP.
Okay, got it. I just needed to start it. Okay, so the whole thing is called the equilibrium expression. This is called the what?
Constant.
Yes.
Oh.
Oh.
And the concentrations, I could say, is an equilibrium position. But we'll get into that. So, does big A, little a, big B, little b, does that confuse you, or are you seeing what it's trying to show you? Okay, yeah, but what is little a in a balanced chemical equation? The coefficient. Does that make sense? Isn't that what comes before your reactant or before your product? So, how you write the equilibrium expression is you always do products over reactants, and then the coefficient of each particular thing gets used as the exponent of that particular thing.
Wait, so that's not the order.
No, this is not a, yeah. No, this is different. Okay? we're gonna do this, you'll find that it almost becomes so easy that you forget some little details, so hopefully we don't do that. Okay, everybody got this? We're gonna do an example here in a second.
So the little numbers are the.
It'll make more sense when we do an actual example, but it's just, this is a generic template showing you that the coefficients of a particular reactant go as the exponent. The coefficient of a particular product go as an exponent. And I'll show you what that looks like on the next page. We good? Can I move on?
Why is the small ones first?
I don't know. Not important. Okay, this is just talking about the law of chemical equilibrium. What this says is, and I said this earlier, if the temperature is fixed, okay, a reaction is going to reach a point, okay, that point is called equilibrium, where the ratio of your concentrations of products and reactants are constant. That's what the constant is. And I said, if the rates are equal, are the concentrations changing? No. So if you take the concentration of your products and divide it by the concentration of your reactants, and neither of them can change, it's always going to give you a what? Did I say that too fast?
Say yeah.
So it really is the product concentration divided by the reactant concentration to a certain exponent, right? At equilibrium, the rates are the same, correct? That's what we said. If the rates are the same, is the concentration of the products going to change? How about the concentration of the reactants? So at equilibrium, if these things don't change, you're always going to get one, what? Oh, that's what this law said. All right, homogeneous equilibrium first. So, homogeneous just means they're all in the same state, as you might imagine from all the times we've been using homogeneous. Okay, I'm going to write the equilibrium expression for this. Here we go. Okay, the constant is KEQ. And then we do products over reactants. It's not overly difficult. Concentration of my product raised to the second power. You guys know where that 2 came from? Right there. Divided by, has a coefficient of 1, so I don't need to write an exponent. Coefficient of 1, I don't write the exponent. What do I do to these two numbers if I knew the concentrations of them? You multiply. Okay, just want to make that clear. There's no plus sign there. That make sense? Okay. That's hard. Now, what if I said KEQ was 4? What could you tell me about the reaction? Product favored. Or the forward reactions favored. Good job. Okay, I want you guys to do this one. Write the equilibrium constant expression for this particular reaction. Go.
Isn't this like correlated?
Are you saying that because I said that 3 seconds ago? Or are you saying that because you weren't listening 3 seconds ago and
No,
you
I
just figured it out?
that.
But it's really important. Here's the thing that I don't want you to do. I don't want you to go, oh, this is so easy, and check out from the fact that it can tell you a lot. Okay? Can the equilibrium constant, the number that you get from the equilibrium constant, tell you a lot about the reaction, where its equilibrium lies? Whether it's product favored, whether it's reactant favored, whether it has a lot, it's really product favored, or just a little bit of product favored. What if KEQ was 1?
They're going to be like equal, or it's the same level as
All of them are equilibrium.
Same concentration.
Sometimes.
If you equal,
Because I could have one squared and the other not. Right?
so what you're saying
I'll
is
show
they
you.
can tell you things sometimes, but not always. Maybe.
Alright, did you guys get this done?
Shoot. Dude, products and reactions. I already messed up.
Is there a way to get this number to be 1 with certain numbers here? But they're probably not going to be the same numbers, are they? So, don't think that an equilibrium of 1 necessarily tells you equal concentrations. It can, but not always.
So what does it tell you? Nothing.
I
It tells you a lot, but it doesn't tell you anything.
I didn't say that. If you get an equilibrium of 1, it's tricky. I'm gonna never give you an equilibrium of 1. It could mean that the concentrations are equal, but not always. Now, if you had like 2 reactants and 1 product and none of them were squared or cubed or anything, then yes. All right, heterogeneous. This is where you have to think a little bit. Right? Heterogeneous equilibrium. Then you're probably thinking, oh yeah, well, you know, it just means that they're not all at the same state. The thing I want to focus on is this. Okay? So we said the equilibrium expression was the concentration of your products divided by the concentration of your reactants, correct? Anybody have any idea, this is a pretty conceptual question I'm asking, why solids and liquids are defined as 1, or basically why you never put solids or liquids in the equilibrium expression? Yes! Not good. Everybody, yes! I mean, I don't know, you said that like it was the easiest question to answer, and it's honestly not an easy question.
I swear.
Good job.
What did she say?
She said the reason why solids and liquids do not appear in the equilibrium expression is because their concentrations can't change. Can you change the concentration of a solid? No. You can't change the concentration of a liquid. Can you compress a liquid?
Yes.
No, you cannot.
To a degree.
I mean, not enough to do anything. Not enough to affect equilibrium, let's say that, put it that way.
Can you change the concentration?
Can you?
Concentration didn't have to do with like the pressing it together.
When did I say that?
I don't know. Like, I thought gauge has something to do with
Don't ever
Okay, so for example, so the 2 things that are important for the equilibrium expression are the aqueous. You guys remember what aqueous is? Dissolved in water. Can you change the amount of solid or substance that you have dissolved in water? Could you dissolve more or less, changing the concentration?
Yeah.
Absolutely. Okay. Could I have a particular gas in a chamber? Okay. And then could I compress the gas, or make it have more volume to change its concentration? Yes. So gas and aqueous concentrations can change. Does that mean that technically, like, could I put a solid in here? Yes. But if the concentrations of solids can't change, it essentially acts as a constant. Doesn't it? So if I take these and multiply by a constant, it's just still going to give me a constant. Okay? So we say, because solids and liquids cannot change their concentration, why even put them in there at all? It's just busy work that you don't need to do. Okay? However, many times on a quiz or a test, students will not look at the phases, and they'll just get trained that products over reactants, and they'll put the solids and the liquids in the equilibrium expression, and I'll have to dock you for it.
So what do you do when there is a solid liquid?
We're talking about it.
See you next time on.
Right? Yeah, we might be trained to products over reactants and do this. Right?
What is that? What's the problem?
You're saying, hey, what? Did I do something wrong?
Is it just one?
It's not one. Can that concentration change?
No.
Now, that's one.
Oh.
No, just
So.
wait, so what are we treating?
Basic.
We're writing the equilibrium expression, but we're not putting in what?
Solids.
Or,
Liquids.
Organic.
Isn't liquids just dissolved in
okay?
water?
So I could put this in, but if it never changes, it's going to give me the same outcome. So just ignore it. Don't put it in. Okay? So, when doing equilibrium expressions, yes, they're easy. They're products over reactants. You take the coefficients, you write them as their exponents. But, if it's heterogeneous, okay, or if it has solids or liquids in it, you make sure that you do not put solid concentration or liquid concentration in the equilibrium expression because they cannot and will not change.
Do we need the plus and minus?
Yes. When doing ions, you must put the charge of the ions in the equilibrium expression.
So you just write the.
Does it affect the math?
Okay.
So that they were just showing you get rid of the AGCL there. So your answer, your final answer is this. Do I need to have over 1? No. Okay. Why don't you guys do this one? Now I realize, is this in your notes?
Yeah.
Okay. Why don't you guys, so in your notes it probably has it more linearly, or more like not below each other. Okay, so why don't you guys attempt to do this? Make sure you put the charge of the ions, they're important. How we doing?
Isn't aqueous dissolved in water? Is that what that means?
Yeah.
Yes.
But if it's dissolved in water.
But we're talking about the ions that are dissolved in water, not the water itself.
Okay.
Does that make sense?
Okay.
So yes, we need to know that it's dissolved in water because that helps us tell us it's in solution, but it still was originally a solid particle or a other particle that got dissolved.
Okay.
So, and because you're dissolving it in water, you could add more of it or take some of it out and vary its what? That's what it is.
61. Wait, is it
Right?
minus?
So I think I just have it here. Did you guys remove the liquid?
Yes.
Yeah.
Everybody? Now, there wasn't any coefficient, so you didn't have to worry about exponents here. Don't forget that. Oh, so, okay. Do this one.
I think you try to do it in your mind. It makes you memorize it more because you actually have to. So like you solve the first part of the problem, then you have to remember that. You can't just write on a piece of paper and then forget about it.
I think
Remember it.
It's also more difficult and harder. That's why, yeah, I'm not like extremely smart. Like I can't do that very well in my head. I cannot picture it in my head. I have to write it down. That's partly why I didn't get a higher score in certain portions of my ACT. This is why a lot of students, I can tell how well they're going to do on an ACT by whether or not they have to write it all down or not. For example, Nathan Long, would you have thought he would get a 32 on his ACT?
Wait.
Kind of a ditzy dude.
What?
Nathan Long got a 32
Oh,
on his
okay.
ACT.
Sorry, I heard that.
Okay? Well, he took physics and got a B, but he never did any work. Never showed anything, never wrote anything down. He was doing all of it in his mind.
Wait, that's how I got it. That's why.
It's not.
It's because I don't write. it
Well,
down.
part of the ACT is speed. And if you don't have to write it down, you can do it all up here, are you gonna be able to do it faster?
Yeah.
I was
See?
thinking
that why I have a bad ACT score?
It is easier.
That's not the
than
only
economics,
reason,
but it's-
but it is a big factor. That's why I
Yeah, but
think
if
someone
you're
like
doing
Isaac
something wrong
Coburn
in
is
math
gonna
all
get a
the
good
time, you
ACT
should
score.
write it down.
I wasn't.
Why is he not
You do
taking it?
sometimes, and it's because you don't write it down.
Yes?
That's true.
Did he get a good score?
But most of the time,
Do you know what it is?
you get anything pretty good.
How many points?
He only got 26?
I mean, that's not bad.
It's not bad.
How many points is it out of?
I thought he said 36. I was
I'm
like,
curious what his breakdown was. I don't know.
He said English.
Okay, that's, yeah. I wish
So he
If-
said it well on the
it's
other
gonna
side.
be- I'm gonna do-
I mean, the science on the ACT is basically reading
The
comprehension.
only thing is.
So it's not really a test of what you know.
Yeah, it's like, which is sad.
Yeah, that's why I didn't do well.
Alright, so did you guys get this? Oops. So it looks like they didn't have an answer, so I'll write it. Okay, EQ. Okay, products over reactants. Notice my product is a. Now, if one's on bottom, you can ignore it, but why can't you ignore the one on top?
Oh.
Good. It wouldn't be a fraction.
Because if you don't have the one on top, it's like saying that your products are your reactants. So, that's why I have this particular problem here. So it should look like that. If I remove the one, the things that were on bottom now miraculously shoot up to the top of the fraction, don't they? Okay? It's important that if your products are solids or liquids, you have to have it in there. Okay? All right. Last thing. Last idea here. Yeah. Well. Okay. I feel like I'm killing you guys on this. Let's just skip that one.
What if it doesn't have a solid liquid gas aqueous? You assume it is.
Alright. Alright, so here's what I want you to do.
Left on
Okay.
Okay.
So I kind of gave you the equilibrium expression for the next problem in your notes. Everybody see it? Okay, it's SiCl4, it's this problem, and I gave you the equilibrium expression. It's up there. Does everybody see it? Alright? Then there's this. This is the equilibrium concentrations. If you know the equilibrium concentrations, you can write the expression, plug them in, and solve for the what? Constant. Okay? So now what I want you to do is I want you to take these numbers, plug them in, and solve for the equilibrium constant. Do you understand what it's asking you to do here?
I think
You're going to put the concentration of HCl in for HCl. You're going to put the concentration of H2 in for the H2, because remember, brackets represent what?
molar.
Molar concentration, so I'm going to take the molarity, plug it in. Not black and white.
Did you remember the exponents? You know, simplify a fraction.
So do you simplify?
Yeah, you do it with
simplify.
the-
So what would you consider a good score on ACT?
Different for different people.
I mean, like, general.
Well, I would say good or average, because there's a statistical average.
What's the average?
I think it's getting lower.
21.
21, I would say, yeah. I would say you can get
It's
24 or above.
Oh, I forgot the
You're-
double count.
Yeah. You're in a good spot. But if you're average, there's nothing wrong with being average. I was average.
I think
But-
the real breaking point though for most colleges for scholarships is like 27, 26,
That's when you start getting
But I got
money. Because that's where you start separating yourself from the rest.
Times
honestly, studying for the ACT actually does help.
Took a 3-hour class yesterday.
On studying for the
Math
ACT.
and sciences.
Okay? But I will say the studying for the best way to increase your ACT score is actually not necessarily to study for math and science.
Well,
It's
that's
to study for English and reading.
Really?
Because
What if you're already good at those? Yeah,
That
what if
was-
your worst is math?
well, yeah, you should study the thing you're worst at. But I'm saying is like English, the English section is going to be the same. You're going to see some of the same questions on every ACT test.
Oh, that's.
Yeah, that's what it
Like, and it's basically just knowing what words are used like feeding sharp. And so if you know, yes.
If it has the cube on the outside of the H2, you have the square.
Yep. So, what'd you guys get for an answer?
0.333333.
1/3 or 0.333. Okay, now
Oh.
interpret that constant for me. What does that tell you?
It's reactive.
That
is favorable.
It is less than 1,
Okay.
so the reverse reaction is favored.
Yes. Write that down.
With reverse.
Reverse reaction is favored. And look at our concentration. Does it suggest that the reverse reaction is favored? Yes. I have more concentration of my reactants, don't I? Same equation. Okay.
Different concentrations.
At different concentrations. So.
Oh, those are our options, okay, I was
Those are your
like, what?
answers.
I was like, what is going on?
One.
Ooh, is it a little bit
Dang it, I can't do this one.
Yeah.
A little bit more tricky.
I'm still gonna try.
A little bit trickier. You guys done over there talking?
We're thinking,
You're trying to do it in your head now too, Marty?
I'm trying.
Brain power
I
here?
can't do, actually,
I think I can do this.
Yeah, I feel like
Watch.
it's just faster using your Why use your brain?
I'm cringing inside.
Joke. So, I
Some
love
people really believe that.
Are you for like who? Like no, but he's not gonna be like this person, this person, this person. People don't actually think that. Like they just do it because they want more.
You're saying they know it's worse for them, but they just knowingly do it anyways?
Yeah.
I mean, you could like weigh all this out.
Oh, that's.
I mean, I could do it in my brain, but it's gonna take longer, and I have more time to comprehend.
You can do 1,296 divided by 320.
Who has an answer?
Clam.
4.01.
Clams?
It's 4.05.
I don't get it.
Oh.
idiot.
Shackles.
Well, I mean, I was reading like
Alright, we're
getting
Shackles.
What's the answer?
Shackles? Number one.
Did you just say shackles?
4.05? Everybody get 4.05.
Yep.
Seeing some head nods?
Yep.
Yep. Okay, what does 4.05 tell you?
The forward reaction is favored.
Now listen. Listen. Didn't I say that if a particular chemical reaction, listen, this is important. This is the same exact reaction, isn't it?
Yeah.
Notice that they have different what? Okay, but I'm more worried about different what? Constants. And didn't I say that all equations will have the same constant?
Equilibriums.
Now, there is another piece of the puzzle that we're going to get to in the future. This has to be at a different temperature. If it were at the same temperature, it would give you the exact same constant. Okay? And we will talk about temperature effects on equilibrium later. But I'm just trying to make the connection that you should have gotten the same constant if it were at the same temperature. Okay, so don't be confused that we got different constant. That means that equilibrium is at a different place. Okay, we'll talk about that in the next couple days.
I have, okay, when we come back Monday, maybe tomorrow, I will have that three books. Okay, and I'll send you the.
I'm not, no, I can't read that fast. Are you for real? I can read that.
By Monday?
Not 170 pages or 870 pages.
I'm gonna read 2,000 pages
In one day?
by Monday. Huh? I'm reading,
Mr.
Christ,
Kramer
Bible.
is
I'm
my dad.
I did.
2,000, that's 2,000.
And
That explains all the spankings.
Oh, spank me, Kramer.
Oh, yes!
and,
Kramer! Kramer! So we have, in college, we have this,
Oh!
we have this leather jumper, that our whole class has to get.
That's the cleanest thing
So-
I've ever seen.
Also, half the English, what did she say?
Oh!
You didn't hit me.
Okay, that's good.
What did you
Oh, sorry for that.
What is that?
This is so
It's not
wonderful.
important. She's like, okay, yeah,
Really?
sure.
Yeah.
I was.
And then I just said, I was like, it's an inside joke.
Oh,
Bucket!
you gotta be gentle.
With 2 G's.
That is good.
Oh!
Last ride.
All you gotta do
I'm gonna do that next time I toilet vlog.
It's really bad if you would have done
Can
that.
we cap the flutter?
Incident.
No.
Oh, yeah.
If we could.
Woo!
I tried.
After you run out.
I was gonna say my name.
For college composition, guess who got Mrs. Safford?
Well, okay, she tossed it. She's like,
Oh,
this is
great.
so weird, and I didn't think it'd be weird. I was like, that's pretty.
Yay.
And she's like, what's old Greg? And we're like, oh, just a YouTube video.
You didn't say that, did you? It's a video we watched on the spring trip. She's an idiot.
She's not gonna look at
She's that.
I will bet.
I will bet.
Okay, no, you're gonna go tell her to look at it. You'd be like, hey, you see what
Why would I tell her to do that?
So you can win the bet.
What are we betting? What are we betting? Let's batter up.
Put an exclamation point.
You know, if she looks at it, then we're gonna be at fault.
That's not worth it though. Not for my job.
I'm betting you $10.
I guess I haven't done 24 hours already.
Mrs. Safford will not mention the video, if that's the video, or comment.
Yeah, because that password's not continually used. Once you use it to get on, you change your password anyway. What's weird?
Oh, a week period? Sure.
She's gonna forget by the time
Guys,
class happens.
Oh shoot, I'm late to class.
Ah, dang it, you wouldn't take it. I wanted a free $10.
Have a seat.
Oh,
You put that back up? Yeah.
I won't.
One day closer.
Right there, bud. You okay?
Old boy, but we got
Well, the thing is, you're using your falsetto.
I know.
He doesn't.
That's why
He just roars.
it's a process.
Wait, we're talking about Bryce Crab.
no, it was like 1
No, we're talking about some guy. You're singing really high.
I don't.
What are we doing with the project?
Hey, we made the
Did you figure out?
democratic decision to get rid of the green slide.
We have, but we've been overruled by a
What's the
dictatorship.
green slide?
Wait, what did you say?
Yeah,
No, why? It's fine. It works fine.
Overruled like the multi-bar.
It's the dumbest.
It's fine.
We are, I need
Just have like polar 8% up.
So we should use that.
What? So we can use the mulch, but we can also make it work.
Yeah, but it's fine with it.
How did it,
Yeah, but what?
because the limit like it said it's cold.
No, there's like 3 people that said
Like,
it.
yeah, that's enough time.
Wouldn't it make sense to find something that's better, that's easier to, like, both better and?
That's true, Bryce. At this point, have anything we really done for this project made sense?
That's true, we, comments.
Double
What?
double.
You're gonna be so proud
So I have yesterday's assignment here. And then assignment here.
Oh, what was it? How that?
Expect nothing less.
You did it one time, it felt so weird, but. You got like.
Those goosebumps.
Gotcha.
Oh, there's a thing there.
It's right on, it's right on the base one, right?
Rose.
How is it I get messed up between potential difference and potential energy.
PE formulas. One of them is.
Well, so like,
Like a math situation?
yeah, because there's that one that was PE equals 1/2 Q or whatever, but then there's also the,
PE equals negative E times Q.
yeah, well, that's, I know, but that's the area, I'm saying like, Q equals, or C equals Q over A, is like how I know we're gonna use that one or the Q.
Last time we were in.
You have to look at it and see if it says energy.
All the way from outside.
I'll have to look at the problems.
I'm about to get a 35.
Can we do it over in I got rid of my snap.
Watch. Watch when I hold it. Once you my hand, that would actually.
Oh, that is weird.
Fail. I can like make a heart.
Okay. Yeah.
My grandma went to movie and she said, the other team right.
No, I'm saying at like 9:20.
Yeah, they.
Or like 10.
It was like no, not. It wasn't that much. And
How
then
much
after
salt?
that, it was a bunch.
And then they just kicked the ball around.
Wait, does it come out?
Yeah.
Is it out? I thought it came out first.
It came out last
Yeah, it was
Yeah, I
eight
thought it
first
was-
half, and then.
But I mean, that's fine.
And then the second half, we got and that was the same with this game. We got eight.
Where are you going?
On Saturday. You're just scared because it's very scary. No, I'm gonna be in this.
I'm ready.
Oh, I guess that's intense.
Here we go. Number one. A and B. 4.8 times 10 to the negative 5th coulombs. Is B 4.5 times 10 to the negative 6 joules.
Oh, is that when we use the PE equation?
There is a P here. So that's your question?
Because I use the same equation for both A and B.
Oh, so you got the same answer?
No, I got this B wrong.
Well, it's probably because you used the same equation for A and B.
No, because I changed the volts, because they
12 cool.
gave you different volts.
I mean, it tells you you're solving for electrical potential energy.
Yeah, and that's my question.
The question is, does electrical potential energy actually mean electrical potential energy?
Like what's,
Or does it mean something?
is that is electrical potential when we use, electrical potential energy when we use the equation of PE in?
Yeah, when it says electrical potential energy, that's PE. When it says potential difference, that's V.
That's, okay.
But, wait.
Because it's like not equal inside. Oh, I didn't have.
Is it like a glass, not glass?
It's like a mirror ball inside glass. It's supposed to be. Did you ever see those one balls where they were like on the TV and they were like making it look like?
Oh, yeah,
They
yeah,
were like
yeah.
putting it over the
Yeah, yeah,
arms.
yeah,
That's
yeah.
like what it is.
I didn't realize it was like a clear one and then a metal ball inside. I don't know. Oh, didn't really think about it.
Number 2. 4.8 times 10 to the negative 6 farads. And B, 5.4 times 10 to the negative 6 joules. So in both number 1 and number 2, You had to find what the Q was for B because the volts change. And if the volts are going to change, your charge is going to change if the capacitor is the same. That makes sense?
Yes.
Like if your capacitor is the exact same and your voltage change, then the number of charge on your capacitor has to change. Okay? So in B, in order to get B, you had to find what Q was under the new voltage.
Would you use C equals Q over G?
Say that again?
Would you use C equals Q over G?
Yeah, so it would end up being, when you would solve for Q, it would be Q would be your V times your C.
Well, number 3, this is about
The whole thing?
Yeah. Number 3, you saw PF and thought it was potential.
Pico's above the,
Yeah.
Pico's above the 9, so we can't use that.
Okay, number 3, so you guys did not know what pico.
Well, no, we
farad
looked it
was.
up when we found it out.
I just say we potential for.
Okay, so yeah, pico is 10 to the negative 12. Okay, so 9 volts and 5 times 10 to the negative 12 coulombs.
Oh, okay. I was gonna say, I thought that was right, but I got it.
Josh, do you have to
The
change
second
the
one.
charge on that one again too? Or the capacitor? I get it. The second answer is always wrong, but barely because I.
Well, this one you would just take your volts times your picofarad.
Well, it should be,
What
is it 2 times 10 to the negative 12 divided by 2.5?
Why'd you divide?
Because that's how you find your, potential difference.
I just helped.
Yeah,
So
you
if
want
it's
to
for
solve for
potential
Q.
difference, then I want
Well, in
the,
B you're looking for Q charge.
I know. So what equation?
It is that C equals Q over V, but you're solving for Q, so you should multiply it.
Oh, right, okay, I
That's
just
what
mixed
you
that up. Yeah, I
divided.
just mixed that up.
Number 4, 1.1 times 10 to the 8 cubic meters. No, meters squared.
Squared.
Sorry.
Like I
I
said.
always mess square and
What is
cube.
this? Times 10 to the 8.
No, because that's not there.
Oh, okay. Did you convert millimeters to meters?
Yeah, and I got .001.
Okay, so you took 1 times 0.001 divided by your that constant 8.85.
I did .001 times the constant, 1 divided by that.
The one on the bottom, that's what it should be.
Dude, what?
Yeah, I set the equation up, right, but.
So C equals E, and then it's A over D, right?
Yeah.
Yeah.
So I multiplied D